Okay, hello everyone, I'm Glenn. How do I change? Oh, there we go. All right, so I'm going to talk to you today about health trajectories. The basic premise is we've got, say, two health trajectories, call them Alice and Bob, and we want to know why it is that Alice bounces up and down, but Bob seems to get worse. So Alice gets bad, she gets better, Bob just keeps getting worse. So what's different about Alice? Nice and simple, right? And the lens through which we look at this problem is in terms of random damage and repair events. So take Bob, he's feeling good, he slips on a banana, and then he can't walk right for a while. That's a damage event, we call that. And then when he gets more or less back to normal, that's a repair event. Some jargon for you, your ability to resist damage, we call that robustness, and your ability to repair, that's called resilience. So we got resilience and repair, damage and robustness. Should be real simple, right? Okay, so we get some longitudinal binary health data, and what that means is we measure a huge number of different health domains, and we make it 0 if there's something, if it's okay, like it's normal or healthy, and 1 if there's something wrong. And then we can, we have HRS and ELSA for that. And then we'll look for the changes. So sometime between age 74 and 76, Bob slipped on that banana, and he had a damage event. Damage event. Well, it'll get there eventually. There we go, damage. Okay, and then we can summarize the overall health based off of the average, that last column. So that's something called the frailty index. So we've got a tool for getting the overall health, that's F, the average, and we're going to look at the ups and downs in the trajectory. So I'll give you some background on the frailty index. It's actually well known. It works pretty well. It increases exponentially with age. There we go. And it's a good predictor of mortality. Okay, so now we've got the y-axis as frailty index, and we're going to try to understand what's different about Alice and Bob. Can we break it down in terms of this repair and resilience and this damage and robustness? So the first thing we ask is, what's different about Alice? She's a bit younger. That could be a big difference. The other thing is maybe there's an effect where Bob gets up high, his damage crosses some critical threshold, and he just keeps going. So there's two really simple variables. It could depend on time. It could depend on the frailty index. Then we're going to use a model to try and parse out what exactly is changing. So I'm going to derive a little model for you. We'll look at the change in the frailty index as just damage minus repair. That's just a matter of undamaged nodes damaging and damaged nodes repairing. And then we can get this nice rate equation, very slowly, ironically. And we take the limit of a small time step, and we're going to get velocity. So the left-hand side is the FI's velocity, how it's changing in age, and the right-hand side is in terms of this damage and repair, and we're going to fit them as random damage and repair events. And what do they look like? Well, we're not sure, so we'll just take the logarithm and say, oh, I'm way ahead. Take the logarithm. Is it oh, you're moving it. Could you go back? Okay, so here. So you've got the logarithm of D and R. That's just to prevent positive and make sure it's positive. And then we just do a Taylor series, and we pick how many terms we need. And I skip ahead, sorry. Go back there. And that's what we get after model selection is the first 3 terms matter. The rest don't seem to really matter. Okay. So what that looks like is on the y-axis, you've got damage rate. On the x-axis, you've got age. It goes up exponentially with age. And as you go from blue to red, the FI also makes damage rate goes up. So we can say that robustness is dropping with age and FI. And similarly, the repair rate is dropping. So resilience is dropping with age and FI. And if you look carefully at the y-axis, you'll see, well, actually, these are going to cross at some point. So at some point, damage is going to outpace repair. And that's probably going to be a really bad thing. And to understand just how bad that is, we go back to our original equation. And we break down the velocity field. So these plots are like wind. So you're at a point here, at a particular age, at a particular FI, you're one of those points. And if you're blue, that means your velocity is negative, so you're going to get better. And if you're red, your velocity is positive, so you're going to get worse. So if you're blue, if you're young, you are up in the top left, so you're going to get better. And if you're red, you're going to get worse. And if you're in the gray, you're going to stay about the same. And you'll see that there's this red line that's delineating those two. That's the null line, where the velocity is 0. And you'll notice on the right-hand side here, you've got, well, on both sides, it jumps up suddenly, that null line. So something horrible is happening right around age 75 that's splitting up 2 age ranges. You've got a low null line when you're young, so you're going to tend towards that red line. And then when you're older, you're going to tend towards the red line, but it's much higher. So you're going to have this older age where it's sort of inevitable you're going to get worse. So we've got 2 distinct dynamical phases. Okay, so then we try to break down how do we understand this in terms of our model. And the key way to do it is to look at the difference in the damage and repair parameters. So I've got this out here. This is just the baseline damage parameters. So baseline difference between your base damage rate and your repair damage rate, that determines where the position of that line will be. So the dotted black line, that is the fit parameter, or that's the fit. And then I'm going to tune near that, and you can see it moves left or right depending on if I make damage more or repair more. And then we look at this time dependence, and that just stretches out time. And we look at the F dependence, and you can see that makes it fan out. So that's what's causing that sharp increase, is this dependence on F. So this loss of robustness and resilience with F. That gives you a critical parameter. If you look in the math, it's exactly 4, and it's right on that value. So nature has tuned it right to criticality, which is pretty cool. That reminds me of something. This is the one-hoss shay that we heard about earlier. Have you heard of the wonderful one-hoss shay that was built in such a logical way? It ran 100 years to the day. At 9:30 by a Meeting House clock, just the hour of the earthquake shock. How it went to pieces all at once and nothing first, just as bubbles as they burst. So you look, when you're young, you get this nice carriage. When you're old, it breaks, and you follow those lines so you get this nice exponential trajectory. The only saving grace is that it's a stochastic process, so if you're lucky, you will have a little bit of delay to it. Okay, so the natural question is then what biologically is changing? And I just want to give you, this is what I'm working on now, and I just want to give you some ideas. So this is the Shen paper, and it's not the perfect paper, but you can see there's thousands of molecules that are all changing dramatically right around that age. So something about age 75 seems interesting. Okay, thank you. This is work from my PhD with the guys on the left, and there's a preprint up if you want to see it. And then I'm moving into the biological mechanisms with the guys on the right. Thanks for listening. I'll take questions.
Thinking more about the biological mechanisms, we've seen in a bunch of different papers that across different sort of layers from molecular to sort of phenotypic, there are these kind of like peaks, different peak periods of change throughout life, and there's sort of one early, and there's one at midlife, and then there's one in late life around 75. Do you think that it's more interesting to look at this peak that happens around 75 during this big shift in frailty, or that changes that happen earlier in life might be setting you up on different trajectories? And is there any way to kind of parse that?
Right, so like when do you really start aging, I guess is what you're getting at.
Yeah.
Yeah, so I mean the insight from the model is that it's a continuous process. It's linear in age, so your robustness and resilience are continuously being lost. So I don't know that there's anything unique about that age in terms of the aging process, but there should be interesting biomarkers of what exactly is happening that things get really bad at that age. If that makes sense. Did that answer your question?
Yeah, I
So I think they both
so.
matter.
Yeah, yeah.
Glenn, when you say things get really bad at 75, should I think about it like if you get injured, instead of getting better, you get worse? So it's like a perturbation test rather than a state test?
Yeah, exactly. So because your net repair is lower than your net damage, anytime you get a damage event, it's just going to stay.
So past age 75, you need to be very, very careful not to fall, to have all the right muscle strength and stability and everything like that.
Yeah, exactly. So it says ramifications for public health. You know, after age 75, you really need to reduce the stochasticity and try to prevent those stress events is what I think.
And has there been any previous notion of that age 75, like from clinical?
No, shockingly no. So the age 65 is for Medicare, and that seems to be purely for historical, political reasons. So, no.
Related to that, if I may. If you look at like risk of various diseases, this always looks like a sort of continuum, and it's not like at 75, then boom, it increases. What are your thoughts?
Right. Okay, so why is it that disease prevalences don't show a similar jump? So the disease prevalences are taken into account to some extent because they're part of that frailty index. There seems to be, I'm not sure exactly, it's exponential. So keep in mind so when you look on, maybe I can show you the last plot and you'll see what I mean. So the velocity field, you've lost robustness and resilience, but you haven't actually got the diseases and the disability yet. So the trajectory you map out is exponential. So you get that same trajectory. So it's hidden until something goes wrong. Okay, thank you.